Right. So in kinetic theory of gases, there are many things. Initially, students think that kinetic theory of gases means as assumption in kinetic theory of gases, but these all four topics involved in kinetic theory of gases, like assumption of kinetic theory of gases and calculation of pressure of an ideal gas, Maxwell speed distribution, Maxwell kinetic energy distribution, and collision theory. So first we are going through assumption of kinetic theory of gases, because in physics and chemistry from many years there are direct statements from these assumptions of kinetic theory of gases, and I have taken all these points, 7 points are there. We have taken all these points from NCRT. So one by one we are going to revise it. So gases consist of large number of identical particles, atom or molecules that are so small, so far apart on the average that the actual volume of the molecules is negligible in comparison to the empty space between them. They are considered as point masses. This assumption explains the great compressibility of the gases. So from this first point, we have to be careful that when we are studying about kinetic theory of the gases, we are taking all the gas particles identical, right? It is not that one gas particle is small in size and the other is large in size. All are identical. Then the second point is they are point masses, right? And that's why whenever we are writing what is the total kinetic energy for a point mass, the degree of freedom, if we discuss, there is only translational degree of freedom. There is no contribution of rotational and vibrational degree of freedom. And that's why in case of gaseous state, we are saying that total kinetic energy is equal to only translational kinetic energy because of these point masses. There is no force of attraction between the particles of gas at ordinary temperature and pressure. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. So, like when they are saying that there is attraction or repulsion, that is not the part of ideal gas. In ideal gas, we'll say that there is no interactive forces, right? So, no force of attraction or no force of repulsion when we are studying ideal gas. The third point is particles of a gas are always in constant and random motion. If the particles were at rest and occupied fixed position, then the gas would have had a fixed shape which is not observed. So gas particles are moving continuously and randomly, and they are moving in a straight line. Particles of a gas moves in all possible direction in a straight line. During their random motion, they collide with each other and with the wall of container. So the pressure developed is because of the gas particle is going to collide with the wall of container. It is pressure is not due to collision between two gas particle, right? It is because the gas particle is going to collide with the wall of container. So these are the points. We know that the same gas can behave like an ideal gas or a real gas depending upon under what condition the gas is there. So we know that if the gas is present at higher temperature and low pressure, means the gas particles will be far apart, right? And at higher temperature it has more kinetic energy, so intermolecular attractive forces is not going to do anything, any effect on the because of high kinetic energy of these gas particles. So we will study in real gas next chapter that under what condition a gas will behave like an ideal gas and under what condition it is going to behave like a real gas. So low temperature, high pressure condition, it is going to behave like a real gas. High temperature, low pressure condition, it is going to behave like an ideal gas. So we are studying ideal gas here. Collision of gas molecules are perfectly elastic. This means that the total energy of molecules before and after the collision remains same, right? So we are saying that collision is perfectly elastic. So kinetic energy is going to be conserved. There may be exchange of energy between the colliding molecules. Their individual energy may change, but the sum of their energies remains constant. If there were losses of kinetic energy, the motion of molecules will stop and the gas will settle down. This is contrary to what actually observed. So we know that during collision with the two gas particles or gas is colliding with the wall of container, the total kinetic energy is going to conserve. At any particular time, different particles in a gas have different speed and hence different kinetic energy. This assumption is reasonable because as the particles collide, we expect their speed changes. Even if initial speed of all the particles are same, the molecular collision will disrupt with uniformity. Consequently, the particles must have different speed which go on changing constantly. It is possible to show that through the individual speed are changing, the distribution of speed remains constant at a particular temperature. So we are going to discuss this point in very detail when we are going to discuss Maxwell distribution of speed, right? So here we are saying that a particular particle can change its speed, but in a particular speed range, the number of particles are not going to change with time. If a molecule have variable speed, then it must have a variable kinetic energy. Under these circumstances, we can talk only about average kinetic energy. In kinetic theory, it is assumed that the average kinetic energy of gas particle is directly proportional to the absolute temperature. So here we cannot talk about the kinetic energy of a particular gas particle because it is continuously changing due to collision with other gas particle. Kinetic energy is not changing due to collision with gas particle and wall, because the direction will all only change, the speed is remaining same, so the kinetic energy is not going to change. Kinetic energy is changing because of collision between two particles, right? Because of their different speed or with different angle, the speed of the gas particle will change. So based on that, we have to study that suppose we have the same gas under two different temperature condition. So in Maxwell equation or in Maxwell distribution of speed, we'll see that at low temperature, this graph is going to be narrow. At higher temperature, this is going to be wide. So the variation of speed is going to change with changing the temperature of the gas. And for the same gas under the same temperature condition, we know that the distribution of speed is like this. We are going to study why the distribution of speed is like this. This is parabolic and this is exponential. This is the speed which most of the gas particles have. This is known as most probable speed, and here it is average speed, and this will be the root mean square speed. So we are going to study about all these things. So in JEE Advanced 2011 paper 1, this is a question according to kinetic theory of gases. It is one or more than one correct. So which of the following option is correct? Collisions are always elastic. Yes. Either it is collision with gas and gas particle or collision with gas and the wall. It is perfectly elastic. So this is correct. Heavier molecules transfer more momentum to the wall of the container. अगर हम B statement की बात करें, if we talk about B statement, this is a correct statement, but they are asking according to the kinetic theory of gases. So when we are talking about the momentum transfer, we know that the gas particle will come and collide if its momentum before collision is m into v. Then after collision, it will become minus m into v, and we can say that the change in momentum of the gas particle is equal to final minus initial, that is equal to minus 2m into v. And the momentum transfer to the wall is equal to 2 into m into v. And so here, from here, if we take average speed, then we can write that this is 2 into m. Average speed can be taken as 8 upon pi RT by m, right? So if I write in terms of mass of one particle in place of RT, I should write KT by m, right? So from here, some of the student are thinking, and they are not wrong, that change in momentum will directly proportional to under root of mass. So more mass means more momentum transfer. But here we have to think that in kinetic theory of gases, all the gas particles are identical. All gas particles are identical. So this statement in general is true, but it is not true with respect to kinetic energy of gases, right? This statement in general is true, but according to kinetic theory of gases, there is no heavier, lighter gas molecules, right? There is only same type of identical particles, right? So that's why B statement is wrong. Some of the students get confused and they have also ticked B. In general, B is a correct statement, but it is not according to kinetic theory of gases. C is only a small number of molecules have very high velocity. So this is correct when we are going to study the distribution of speed, Maxwell speed distribution. The graph is like this. Here, this is dn upon n du. Dn upon n is the fraction of particles in a particular speed range du, and this is u. And the graph near the origin, it is a parabola, and as we move away from the origin, it will be exponential graph. So the nature of the graph is like this. So very high speed, the fraction of particles will be low. Very low speed, the fraction of particles will be low. Most of the particles is at near about whose speed is equal to umps. Most of the particle is near about umps speed. So here the C statement is correct. This statement, between collision the molecules move in a straight line with constant speed, that is correct. This is the assumption. We are assuming point mass and we are saying that they are moving in a straight line, and because of that we are writing total kinetic energy is equal to total kinetic energy is translational kinetic energy of gas particle, because these are point masses. So this statement is also true. So the answer for this will be A, C and D. So most of the student get confused. So that is important. All the gas particles are identical. The next question, JEE Mains, that is a theoretical question. That's why it is important. Which of the following is not an assumption of kinetic theory of gases? Gas particles have negligible volume. Yes, they are point masses, so they have negligible volume. So this is a true statement. We have to say that, which is not a true statement. A gas consists of many identical particles which are in continual motion. This is also true. At high pressure, gas are difficult to compress. Means repulsion, attraction and repulsion is related to real gas. It is not related to ideal gas. High pressure gas particles difficult to compress. This is not the assumption in kinetic theory of gases, right? So here this statement will be a false statement. Collision of gas particles are perfectly elastic. This is a true statement. So be careful. Though this statement is true, but this is not related to kinetic theory of gases. So those 7 assumptions are very important. Careful, you should be careful about that. Now, calculation of pressure of an ideal gas. So there is a derivation. We are not going to do the derivation, right? I will share the notes. You can go through that. So for an ideal gas, we know that there are two equations. One, we write that PV is equal to nRT, and the other equation is PV is equal to 1 by 3 small m into capital N into U square mean, right? So these two equations are very important. Here, calculation of pressure of an ideal gas, we are talking about this equation, and here it is derived. So please go through the derivation. It is also important for physics, but we don't have time to do all that. So this is the derivation. With the help of this derivation, what are the important points which we can derive from using the equation? So using this equation, PV is equal to 1 by 3 mn u square. Prove that the root mean is square speed, right? Because from here we can say that this is mean square speed. And from mean square speed, we can write that this value is equal to 3 times of PV upon mn. And PV is equal to nRT, right? So by using that, we can write here capital N is the total number of particles, which is Avogadro number into number of moles, right? So if we take Avogadro number and mass of one particle, this is molar mass of the gas, and from there we can derive that U square average means mean square speed is equal to 3 RT by M, and from there we have done the derivation. While solving the question, be careful about the units, right? So you already know about these things. I'm telling that the derivation of mean square speed or root mean square speed can be done with by using this equation. And using the two forms of ideal gas equation, prove that total kinetic energy or total translational kinetic energy is equal to 3 by 2 nRT, and average translational kinetic energy is equal to 3 by 2 kT. So since we have considered point mass, that's why total kinetic energy is translational kinetic energy. So we can write that total kinetic energy is equal to half into m into speed of first particle whole square and so on. And by simplifying it, we can write that total kinetic energy is equal to this. Important question in JEE Advanced and Mains, they have already asked that average kinetic energy only depends on absolute temperature, but total kinetic energy depends on number of moles and temperature. So it is an extensive variable. Total kinetic energy is an extensive variable, but average kinetic energy only depends on temperature. These are constant. So temperature is an intensive variable. So this average kinetic energy is intensive variable, but total kinetic energy is extensive variable. So based on the equation we have studied, this is a question, right? So you can solve this question for a given gas containing 10 to the power 23 molecules. This is the total number of gas particle or molecules, right? Each having a mass. So mass of one particle is given, that is 10 to the power minus 22 gram. And the volume of the container is 1 decimeter cube, means 1 liter. Calculate the total kinetic energy of molecules if their root mean square speed. So this is given root mean square speed, that is equal to 10 to the power 5 centimeter per second. We have to calculate the temperature of the gas in Kelvin. So we can write this equation, PV is equal to 1 by 3 small m into capital N into U square mean, and PV is equal to RT. So from there we can calculate that what is PV is equal to nRT. So from there we can calculate what is the temperature by putting these values. So be careful while putting the data over here. So I can write here that the mass we have to write in kg, right? And the volume we have, if we are using this equation to calculate the pressure, but here we have to calculate temperature. So number of particles is known, mass we have to keep in kg, and this in meter per second, this is in centimeter per second. So by putting all these, we can calculate the number of moles also, because if we divide this value by Avogadro number, we'll know that what is the number of moles, and we can simplify. For simplification of calculation, they have given the value of R and Avogadro number. So very simple question. Based on this formula, you can apply and solve it. So right, you can apply in this way and you can solve it. Okay. So moving to the next problem, JEE Advanced 1997. I'm talking about average translational kinetic energy only depends on absolute temperature. The average translational kinetic energy of O2, whose molar mass is 32 molecule at a particular temperature, is 0.048 electron volt. The average translational kinetic energy of nitrogen, whose molar mass is different in electron volt at the same temperature. They are talking about average kinetic energy. Average kinetic energy only depends on temperature. So if two gases having different molar mass but temperature is same, their average kinetic energy is going to be same. This is also the same question based on the formula PV is equal to 1 by 3 mn U square mean. So be careful about this equation, right? This is very useful. Okay. So now we are discussing Maxwell distribution of molecular speed, and this is very important. It is assumed that in coming years, right, the question, a very good question can ask from this theory. So there are certain assumptions in Maxwell distribution of molecular speed. The speed of a molecule of a gas is continuously changing as a result of collision. Therefore, we cannot speak about the speed of individual molecule. So here we are discussing about average speed of the molecule. Different type of speed is there. Most probable speed, average speed, and root mean square speed. We cannot talk about speed of an individual gas particle because it is continuously changing due to collision with the gas particle with another gas particle. Since the observed properties like pressure and average kinetic energy do not change with time, it is expected that it would be possible if the number of particles between any definite range must remain constant, even though the speed of individual particles may be changing continuously, right? So we can divide the total gas particles into different speed range, and the number of particles in this speed range with time is not going to change, or this speed range with time is not going to change, or this speed range with time is not going to change. It may possible that some of the particles will change their position from here to here, or here to here, or here to here, but the number of particles in a particular speed range is not going to change. So Maxwell is equation of distribution of speed. This equation is not in our JEE syllabus, but I have to explain many things using this equation. That's why I am using this equation. And if possible for you, if you remember, then it is fine. You don't have to remember this, right? So what is this Maxwell distribution of speed? We are writing that dn is the number of particles in the speed range u to u plus du. In a particular speed range, dn particles are there, which is equal to 4 pi n m upon 2 pi rt to the power 3 by 2 exponential minus mu square upon 2 rt u square du, right? So you don't have to mug up, but agar aapko yaad hai to it is fine. With the help of this equation, I am going to explain many things. So this is dn. Dn is the number of gas particles in a speed range u to u plus du. N is the total number of gas particle. M is molar mass of the gas. R is universal gas constant. T is the temperature of the gas in Kelvin. And u is the speed of gas particle. Now I want to simplify this equation in terms of small m. Capital M is the molar mass. I want to write in terms of mass of one gas particle. So capital M can be written as small m into Avogadro number, right? And R upon Avogadro number will be Boltzmann constant. So here if you see 4 pi will be there, right? Dn upon n, and capital M is written as small m into Avogadro number, and R upon Avogadro number is Boltzmann constant. Again here we put capital M is equal to small m into Avogadro number. So R is replaced by Boltzmann constant. So this equation or these equations are the same thing. Now we want to explain the graph, right? So here what we are assuming that on the y-axis, we have assumed that y is equal to fraction of particles in a speed range du. So this is dn upon n du. This is Maxwell distribution function, right? And this is the speed of the particle. So if we try to write that at a particular temperature for a fixed amount of a gas, right, and gas particles are identical, so we can say that at a particular temperature this whole thing 4 pi m upon 2 pi rt to the power 3 by 2 will be a constant. This constant is a, and b is m upon 2 rt. So we know this is the equation. If I take dn upon n du on this side, this is the Maxwell distribution function, and this whole thing 4 pi m 2 pi rt to the power 3 by 2, this we have assumed a, and here m upon 2 rt is assumed b. This m upon 2 rt is assumed b. So I can write this equation as y is equal to a exponential minus b x. Yeah, speed is assumed to be x, so x square, and here it will be x square. So there are two things. One is parabolic, right? Here y is directly proportional to x square, and this is exponential. So the curve at any temperature is parabolic near the origin. So when the value of x is small, this part is dominating, so this is parabolic. And as we move away from the origin, this exponential part is going to be dominating. So in dono ko milake, this is the curve, right? So here this parabola ki jo axis hai, right, that is y axis. Now from here we can derive some important point. The first point we are going to derive here is if we draw Maxwell distribution function versus speed graph, where Maxwell distribution function is dn upon n du. right? Then we can say that area under the graph is equal to 1. So here on y-axis, this is Maxwell distribution function dn upon n du, and this is a speed. And if we take a small strip on this curve, so the change in x is very small, so y remains almost constant. So area will be, this is looking like a rectangle, so length into width will be the area. So this du will cancel out, and this is dn upon n. So this is fraction of particles in this strip. So if we integrate from here to here, we'll say that we'll write all the fraction of particles in different speed range. So the denominator remains constant. This is variable dn1, dn2, dn. So if we add all these, this will become n. So n upon n is equal to 1. So this is, if on y-axis, this is Maxwell distribution function versus Maxwell speed, area under the graph is equal to 1. We have proved mathematically, right? Now, some of the students get confused. Sometimes the graph is dn upon du versus u. So this is the number of particles in a particular speed range. This is not the fraction of particles. So again, here we take a small strip. Again, the width is small. So change in y will be very less. So it will look like a rectangle. So multiply these two, dn upon du into du. So this will be dn. This is the number of particles in a particular speed range. If we take summation at different ranges and add all of them, then it will become dn1 plus dn2. So we'll get total number of gas particles. So under this graph, area under graph is going to be total number of gas particles. So be careful while answering the question, right? If the graph is like this, the area under the graph will be 1, right? If it is Maxwell distribution function dn upon n du, and if it is dn upon du, it is going to be capital N. Then prove that most probable speed, right? So here we are saying this is the function, and we can say that this height is representing the maximum value of the function. So corresponding to this maximum value of the function, this speed is known as most probable speed. So in a container, the particles having very low speed is less in number. The particles having very high speed is less in number. Most of the particle is near, are those particles whose speed is near to the most probable speed. So in this function, if we have to find out what is the maxima, for maxima we say that dy by dx is equal to 0. So in this function, if we differentiate it and put it equals to 0, the function is this. If I differentiate it with respect to x and put it 0, I will get that the value of x at which the function is maximum, that x is under root 2 RT by capital M. So this speed is known as most probable speed. तो आपको ये पता होना चाहिए, you should have a feel that what is most probable speed, and this most probable speed formula can be derived from Maxwell distribution of speed, equation of Maxwell distribution of speed. Prove that you don't have to remember the proof, but I'm just telling that u average का formula आपने पढ़ा है, that is under root 8 upon pi RT by M. So this u average can also be derived from this Maxwell distribution of speed, because when we have to write average speed, we'll take a number of particles having speed u, and this speed can be vary from 0 to infinity, and we divide by total number of particles. So if we put here dn from the Maxwell equation and try to simplify it by using this integration result, we can prove that this value is equal to under root 8 upon pi RT by M. I am saying that don't remember it, just remember the formula of average speed, which you know, right? But this speed can also be derived from Maxwell distribution of speed. Now, comparison between different type of speed for the system we are discussing here. Root mean square speed, which we have determined the formula of root mean square speed is equal to under root 3 RT by capital M. So using PV is equal to 1 by 3 mn u square mean, we have derived that, but we can also derive with the help of this Maxwell equation. So URMS, then U average. U average means you add the speed of all the particles divided by the total number of particles, and U most probable speed. All these speed you know. So you know that this U most probable speed formula, you know, that is equal to under root 2 RT by M, right? Then U average is under root 8 upon pi RT by M, and U RMS is under root 3 RT by M. Most of the student only remember this, or they can simplify this. But in exam, if you see, these datas are simplified and then they have used. So it's very easy to remember, right? It is 1 is to 1.128 is to 1.22.4 is very common to us, right? So from there we can. So this is URMS, this is U average, and this is most probable speed. JEE means JEE advanced में we have directly used this formula to solve the question. Please try to remember it because it is difficult to solve in exam. So now from this graph, if you see, this is the fraction of particles in a particular speed range. So you can see that if we are talking about most probable speed, the height is maximum. Then at U average, the height is less. And at URMS, the height is least, right? Among these three speeds. So here we can say fraction of particles having UMPS is greater than fraction of particles having U average is greater than fraction of particles having URMS. So this is also the relation. And it is very important to understand that all the speed is directly proportional to under root T by M. Now we are going to prove that all these fraction of particles in a particular speed range is directly proportional to M by T. तो ये T by under root T by M है, and this is directly proportional to under root M by T. We are going to prove this further. So the first point which is important regarding the graph, this is the function, Maxwell distribution function. It is a function which depends on molar mass upon temperature ratio, right? Because whenever we are writing this is a constant A, this constant A is directly proportional to M by T to the power 3 by T. So it is a function of M by T. And the function B we are writing that B is equal to M upon 2 RT. So again, it is a function of M by T. A and B is a function of M by T. That is an important point. So if M is same but T is different, then the graph is wide at higher temperature and narrow at lower temperature, or increasing the temperature for a gas, the fraction of molecules having U MPS will decrease, and the fraction of molecules having very low speed will decrease, and the fraction of particles having very high speed will increase. UMPS will increase on increasing the temperature. It's very simple and logical to explain. One thing is that this Maxwell distribution fraction or function dn upon n du is directly proportional to under root of m by t, while the speed is directly proportional to under root t by m. So you can see here that this is the speed, and corresponding to maximum height at lower temperature, we are writing the speed. Speed is directly proportional to under root temperature upon molar mass. So suppose if we are saying that gas is same, if the gas is same at different temperature, we want to study the graph. For speed, you can see that as the speed is increasing, temperature UMPS, you can check here that this is lowest value of UMPS when the temperature is 200 Kelvin. Then at 300 Kelvin, it is increasing. At 500 Kelvin, it is more increasing, and so on. So as you increase the temperature, UMPS is going to increase for the same gas. When we are talking about this height, we are writing that the height is directly proportional to under root m by t. So for the same gas, molar mass will be same. As we are increasing the temperature, this height is going to decrease, right? So the graph will be narrow at low temperature, and the graph will become more and more wider at higher temperature. Now we are discussing that for a same gas, if we are changing the temperature, what is happening? On decreasing the temperature, the fraction of particles in low speed range is going to increase. So अगर मैं temperature को decrease करता हूं, तो fraction of particles in low speed range is going to increase. In high speed range, we can say that as we increase the temperature, the fraction of particles is going to increase. In high speed range is going to increase. So these are the questions which can be discussed from here. Now moving to the next point. At a fixed temperature, the graph will be narrow for a heavier gas and wide for a lighter gas. Using the same condition, you can see here that this is narrow, right? And you can see that helium, neon, and xenon. So this color is for xenon. For a heavier gas, because temperature is same here, we are discussing for different gases at the same temperature. So this is narrow, then this is further wide for neon gas, and this is further wide for helium gas. So lighter the gas, wider the graph, heavier the gas, narrow the graph. Again, here we can discuss that in low speed range, heavier the gas, more will be the fraction of particles, right? And in high speed range, we can say that as the speed is going to increase, for lighter gas particles, we can say that the fraction will be more. The heavier gas particles, the fraction will be less. So there are fixed type of question based on distribution of speed. We are going to discuss these question. Find the fraction of particles lies between UMPS to UMPS plus du. So we are taking a particular speed range here. UMPS is there, and range UMPS to du. So the range will be du only. So near here we are discussing. So by using this equation, we can write that dn upon n is equal to 4 pi m upon 2 pi rt to the power 3 by 2 exponential. स्पीड की वैल्यू यहाँ पे है UMPS. If you put minus m upon 2 RT, u square will be 2 RT by m, because root mean most probable speed is under root 2 RT by m. So most probable speed uh, whole square, if you put, right, so this will be 2 RT by m. So it is independent of molar mass and temperature. U square will be same, and du here. So if you simplify this, agar is pure ko aap simplify karo, so we can say that dn upon n, these are constants, right? Dn upon n depends on three factor. This is directly proportional to under root molar mass of the gas upon temperature into du. This depend on these factors, right? So find the fraction of particles lies between UMPS to UMPS plus fractional part of UMPS. This du is equal to fractional part into UMPS. So if you put like this and simplify, you will get that this dn upon n fraction of particles is directly proportional to that fraction. It is independent of molar mass and temperature of the gas. So this conclusion is important. When the speed range is a fractional multiple of UMPS, then it is independent. The graph nature is independent of molar mass and temperature of the gas. Similarly, find the fraction of particles lies between URMS to URMS plus du. If this is like this, then we'll say it depends on three factors. It depends on directly proportional to molar mass upon temperature and directly proportional to the speed range. This constant is different from what we have taken for UMPS. For UMPS, the constant will be different, but for URMS, the constant is going to change. But the variables will remain same, right? So same type of conclusion you can make here, right? Now, if this du is a multiple, fractional multiple of URMS, then again this m and t will cancel out, and this fraction only depends, this dn upon n only depends the fractional multiple of URMS, right? It is the only variable here. So it is independent of molar mass and temperature of the gas. Similarly, for the third speed, U average, you can find out the same type of conclusion, that dn upon n is directly proportional to under root molar mass upon temperature into du. But if du is fractional multiple, then this m and t will cancel out. It only depends on this fractional multiple. So based on that, there are questions, right? Like one question, theoretical question they can ask, if two gases having the same value of m by t, then the dn upon n du versus u graph is identical for them. For example, if we take oxygen gas whose molar mass is 32 and temperature we have taken 300, so this is m by t for oxygen gas. If we take sulfur dioxide gas whose molar mass will be 64 and the temperature is 600 Kelvin, so for sulfur dioxide gas and oxygen gas, the value of m by t will be same. So both gases have identical graph, right? Both the gases have identical graph. So based on that, there is a question. So I'm not going to solve the whole question, but here, like B, C, and D part are very simple to solve, and they can come in JEE Advanced also, because we have already discussed the nature of graph and all that. For A option, the chances are very less, because for that you should know what is Maxwell equation. right? So here let us focus on this. The ratio of dN upon N for O2 and SO2 gas lying between URMS to URMS plus dU at the same temperature. Temperature is same, means it depends on molar mass of the gas. And they are taking this both for both gases, they are discussing about URMS and URMS plus dU. So the constant will be same. So we can write that the fraction dN upon N is directly proportional to uh, molar mass upon temperature into du. Du is same, temperature is same, is dN upon N is directly proportional to molar mass of the gas, right? So and these constant will cancel out because constant are same. So we can say that dN upon N, molar mass of O2 gas upon molar mass of SO2 gas, and we can simplify that. That will come 1 by under root 2, right? So B should be matched with Q. Similarly, the ratio of dN upon N for O2 and SO2 lying between UMPS to UMPS plus du. Again, we are going to use the similar type of formula, but only the constant is going to change. So here there are two gases and UMPS plus du, range is same, temperature is same. So again, we can say that this ratio is also equals to 1 by root 2. Ratio of dN upon N for O2 and SO2 lying between U average to U average plus fractional multiple of U average at the same temperature. When you are writing fractional multiple of U average, it is independent of molar mass and temperature. And the range here will be same for both the gases. So we can say that this is directly proportional to the fraction, and the fraction is same. So the ratio is going to be 1:1. So इसका जो आंसर होना चाहिए वो P होना चाहिए. For this, you should remember, because it is out of syllabus, I am not discussing it. But if you want to solve, that is very simple. You can solve by using this equation dN upon N, or dN is equal to 4 pi N M upon 2 pi RT to the power 3 by 2 exponential minus mu square into du. If you remember this equation, you can simplify it, but it is out of syllabus, right? Maxwell distribution of kinetic energy. This is also given in NCERT. NCERT में ये indirectly इस पे graph given है. Chemical kinetics में we are discussing kinetic energy graph, fraction of particles and kinetic energy graph. So by using Maxwell equation, we can derive an equation for distribution of kinetic energy, because we know that kinetic energy of one gas particle is denoted by epsilon, and that can be written as half into mass of one particle into speed of that particle whole square. If we differentiate on both sides, we can get that change in kinetic energy is equal to half into mass into 2 times of u into du, and then we can further simplify this, right? So here on simplification, we can write that this is the equation for distribution of kinetic energy. I'm not saying to remember all these things. I'm telling that with the help of this, we can explain the graph given in NCERT, and whatever the conclusion we can make from here is important. So this is the distribution of kinetic energy of gas particles. So by the same way, if we try to write that this is the fraction of particles in a particular kinetic energy range, that is equal to y. And here the kinetic energy of a particle is x variable. And this whole thing will be a constant, and this thing is also a constant. So with the help of that, we can write this equation. इससे पहले जब हमने स्पीड की इक्वेशन लिखी थी, दैट वाज y इज इक्वल टू a इंटू एक्स स्क्वायर एक्सपोनेंशियल माइनस b इंटू एक्स. इट वॉज लाइक दिस, राइट? ये वाला ग्राफ था. तो ये पैराबोलिक है. हियर ऑल्सो दिस इज पैराबोलिक, बट आप देख लो कि y इज इक्वल टू एक्स स्क्वायर में एक्सेस विल बी y, एंड हियर y इज इक्वल टू अंडर रूट एक्स में एक्सेस विल बी दिस एक्स एक्सेस. तो जब हम ये स्पीड वाला ग्राफ बनाना है तो ये y एक्सेस की तरफ है, एंड दिस इज गिवन इन एनसीईआरटी. ये जो पैराबोला है इसका एक्सेस जो है वो x एक्सेस है, एंड दिस इज द एक्सपोनेंशियल पार्ट. So this graph is given in NCERT, right? And same way, with the help of this equation, we can find out most probable kinetic energy. This height is most probable. The kinetic energy with respect to this height is most probable kinetic energy, right? So you can prove by using this, because here the function has maximum value. So we can say that dy by dx is equal to 0. by using this equation, by putting dy by dx is equal to 0, we can prove that the most probable kinetic energy is equal to kt by 2. This is the most probable kinetic energy, because average, average you write 3 by 2 kt. So this is most probable kinetic energy. So they can ask question regarding these two relations, right? So here this is most probable kinetic energy, and you know that why the nature of this graph is towards x-axis, right? And all these things you have studied in chemical kinetics, or you will be studying in chemical kinetics. So that is the point. So find the fraction of molecules having kinetic energy in the range ump to ump plus de, right? So मतलब यहाँ पे ये kinetic energy range है, and by using this equation you can prove that dn upon n is directly proportional to the kinetic energy range and inversely proportional to temperature. And we know that at low temperature the graph will be narrow, at high temperature the graph will be wide, like that. So this most probable kinetic energy is going to decrease on increasing the temperature. अगर आप most probable kinetic energy की value देखो, it is going to increase on increasing the temperature, but the fraction, this is the most probable kinetic energy, but the fraction is going to decrease on increasing the temperature. So low temperature पे narrow graph, high temperature पे wide graph. Same type what we have studied for distribution of speed, the same type of things are given for distribution of kinetic energy, right? So the graph of distribution of kinetic energy uh, is narrow at low temperature and wide at high temperature. On increasing the temperature, the most probable kinetic energy will increase, and the fraction of molecules having most probable kinetic energy will decrease. The area under the graph is equal to unity. So JEE Advanced में this was the question asked. If the distribution of molecular speed of a gas as per the figure given below, then the ratio of the most probable average and root. So I have told you that you should remember that UMPS is to U average, U is to U RMS. This is 1 is to 1.128 is to, ये तो आसान है, 1.22.4, right? So this is the ratio. Now when we are drawing this graph, it is not a symmetric graph, right? If you see, parabolic path is dominating near the origin, and then exponential part is dominating away from the origin, and if we connect, this is the graph. So it is not a symmetric graph. So this is the ratio when the graph is not symmetric. In this particular graph, it is very symmetric. So when we calculate the average speed, suppose if I am calculating the average speed, so it is at this point, right? Because it is symmetric, you can see that the average here and here will be this, the average of this and this will be this, the average of this and this will be this, right? So when we are going to derive the value of average speed, the average speed and most probable speed is going to coincide, right? And that's why the ratio is 1 is to 1 is to 1.224. So this cannot be possible. This will be possible when the graph is like this, right? And here this is also wrong because these two cannot be possible, right? Here if the graph is symmetric, then most probable speed and average speed is going to be same, and because of that we can say that the answer for this will be B. B should be the answer for this. So the next question, which of the following change can be made in order to double the RMS speed of a gas kept in a rigid container? Rigid container means volume is constant, right? Volume is constant, and we know that VRMS is directly proportional to temperature by molar mass, or we can say VRMS is equal to 3RT by capital M. So gas is same, so molar mass is going to be same. So double the temperature by heating the gas, we have to double speed. So if we increase the temperature 4 times, then it will be double. So A option will be wrong. Increase the pressure 4 times. Volume is constant. We can say pressure is directly proportional to temperature. If you increase the pressure 4 times, you are increasing the temperature 4 times. If you increase the temperature 4 times, speed will be doubled. So this seems to be correct. Increase in pressure 4 times by heating the gas. increase the pressure, decrease the pressure by removing some gas. On decreasing pressure and you are removing gas means uh, you can write PV is equal to nRT. You are not changing the temperature, you are removing the gas. That's why pressure is decreasing. So if you don't change the temperature, RMS speed is not going to change. Increase the pressure 4 times by pumping some gas. Again, this is not valid. Volume is constant and you are increasing the number of moles. That's why pressure is increasing. You are not changing the temperature. So this is also false. Only the correct statement will be B statement. The graph below shows the distribution of molecular speed of two ideal gases X and Y at 200. On the basis of the below graph, identify the correct statement. So this is fraction of gas particle and this is speed. So this height is more. So we'll say that this graph is narrow. That will be narrow at low temperature, or that for heavier gas. So we'll say that X should be the heavier gas, right? And this graph is going to be wide for a lighter gas. For lighter gas, it is going to be wide. If you forget about those things, you should remember that U is directly proportional to under root T by M. And this fraction is directly proportional to under root M by T. So from there also you will be able to know. So if gas X is methane, X gas is heavier gas. They are saying that if this is methane, then the Y gas should be lighter than methane. Carbon dioxide is heavier than methane. So first option will be wrong. Fraction of molecules of X must be greater than Y in a particular range of speed at 200 Kelvin. They have not mentioned the speed. If we take low speed range, in low speed range, the fraction of particles of gas Y is greater than gas X. In high speed range, the fraction of particles of gas Y is greater than gas X, right? So you have to mention under what speed range we are discussing, then only we can answer it. It can go both ways, right? So that's why this is also wrong. Must likha hai. Because of that, it is going to be wrong. Under identical condition, rate of effusion of gas Y is greater than rate of effusion of gas X. Rate of effusion or diffusion, if we say, that is directly proportional to number of particles per unit volume. It is directly proportional to area of the hole, and it is directly proportional to average speed of gas particle. If we simplify all these, we can say rate of effusion depends on four factors. It is directly proportional to pressure of the gas, directly proportional to area of cross section, and it is directly proportional to, inversely proportional to under root molar mass and temperature. If you simplify this, you are going to get this, right? So now under identical condition, they are asking means pressure, temperature and hole will be same. There are two different gases. So we can say it is inversely proportional to molar mass, right? So under identical condition, rate of effusion, lighter gas will effuse more faster, right? And the lighter gas here will be Y. So rate of effusion of Y is greater than that of X. This seems to be correct. The molar kinetic energy of gas X at 200 is equal to, molar kinetic energy formula is what? That is equal to 3 by 2 nRT. If we are talking about molar kinetic energy, it will be 3 by 2 RT. It only depends on temperature. Both the gases are present at the same temperature. So their molar kinetic energy of gas X and gas Y is going to be same. So answer for this will be C and D. This is J Advanced 2019 question. So which of the following statement is are correct regarding the root mean square speed and the average translational kinetic energy of a molecule in a gas at equilibrium? URMS is double when the temperature is increased 4 times. This seems to be correct because any type of speed is directly proportional to under root of temperature. U average of a given at a given temperature does not depend on the molar mass of the gas. That is also correct. Average kinetic energy is equal to 3 by 2 into kT. It only depends on temperature. So this is also correct. URMS is inversely proportional to square root of molar mass. We can write URMS any type of speed, right? That is equal to 3 RT by capital M. It is inversely proportional to molar mass of the gas. This seems to be correct. Average kinetic energy is doubled when the temperature is increased 4 times. It becomes 4 times, right? Because it is directly proportional. So this statement will be wrong. So answer will be 1, 2, and 3. So based on the theories, you have to very careful about these theories. Right now, we are going to discuss about bimolecular collision, which is also very important. While considering collision, we assume that the molecules are rigid and non-reacting with diameter sigma. All the gas particles are identical, right? So they all have same diameter. It is assumed that all molecules move with the same speed because we know that all particles are continuously changing its speed. So it is difficult if we want to study one particle. So for simplification, because average kinetic energy or average speed is not going to change with time, when the temperature and gas will remain same, right? So that's why this assumption we have taken in order to make some equation. It is necessary, it is assumed that all molecules move with the same speed, which is average speed of the system. So you know collision diameter. Collision diameter is the distance between the nuclei of two gas particles at their nearest approach. So that is equal to the diameter of one gas particle because both the particles are identical. So this is collision diameter. Then collision cross sectional area. We are considering bimolecular collision only, means at a time only two particles can collide. So when these two particles are colliding, no other particles can enter in this region. So this whole region is occupied by these two particles only, right? And if we take projection of that, this will be a circle whose diameter is going to be sigma. So collision cross sectional area is equal to pi into sigma square. So this is collision cross sectional area. What is the application of collision cross sectional area we are going to discuss, right? We should also know that what is co-volume. Co-volume or excluded volume is denoted by B. It is the volume occupied by 1 mole of real gas particle. We know that ki yahan pe these two particles are occupying a total volume of 4 by 3 pi into 2r whole cube. This is the volume occupied by two particles. So it is 8 times the volume of one particle. 8 times 4 by 3 pi r cube. So this is occupied by two particles. So for one particle, the volume will be 4 into 4 by 3 pi r cube. When we are talking about excluded volume, volume occupied by 1 mole of real gas particles. So we should multiply here by Avogadro number. So many of the students remember that this is volume occupied by 1 mole of real gas particle, but they forget the factor of 4, which is important. So now we are discussing what is collision number. First, you should not confuse with collision number and collision frequency, because Atkins में जो language दे रखी है that they have reversed it, right? In place of collision frequency they are using collision number, but in NCERT we have to follow NCERT because the question frame by taking the language of NCERT. तो जेई एडवांस में जो भी क्वेश्चन पूछे गए हैं एनसीईआरटी के हिसाब से कोलिजन नंबर का मतलब है इट इज द टोटल नंबर ऑफ बाईमोलिकुलर कोलिजन बाय वन पार्टिकल इन यूनिट टाइम. So many of the students try to mug up this formula. If you try to mug up, you will forget after some time. Try to mug up with the help of derivation. That's why I'm focusing more on that. What we are saying that this is the whole container. There are n particles and the volume of this container is capital V. So number of particles per unit volume in this container is n by V. What we are saying here that a particle is moving, this particle, whatever this hypothetical particle is moving with average speed, distance traveled by hypothetical sphere in unit time. So that is equal to the average speed of the particle. So what is the volume covered? We can neglect this volume, right? Because this volume is very small. So what is the volume covered in unit time? This is the volume covered. So that is area, collision cross sectional area into U average. So this is the volume covered by this hypothetical sphere, which is representing bimolecular collision in unit time. So we can calculate that. So while calculating this, we can assume that only one particle, this is hypothetical thing, we are assuming that only one particle is moving with average speed and all the particles are stationary, which is not correct, but this is hypothetical. So hypothetically, we are assuming that only one particle is moving with average speed and other particles are stationary. The volume covered by hypothetical sphere in unit time is pi sigma square into U average. This is the volume covered because this is collision cross sectional area and this is the distance. If we multiply by this into this distance, this volume we are writing here. Now by using unitary method, that in V volume n particles is there in unit volume, number of particles per unit volume. So if this is the volume covered, how many particles will be there in this volume? That is n by V into pi sigma square into U average. So this is Z1. This is in hypothetical condition when one particle is moving and all the particles are stationary. But in actual, all the particles are moving and we have assumed that all of them are moving with average speed, and they can collide with each other. Head-on collision can be possible, or when one particle is going, another particle will come from behind and they can collide. So the angle by which they can collide varies from 0 to 180 degree. These are the angles. So if we take average angle of collision, that is equal to 90 degree. So in general, we are saying that the mean angle of collision is 90 degree. So if both particles are heading towards each other at 90 degree, we can find out what is the relative speed. In relative speed, one particle will be stationary and the other particle will move with that relative speed. So the value of relative speed or net speed is equal to under root 2 times of U average. So while doing the actual calculation, we'll say that the collision cross sectional area is pi sigma square, and the distance traveled by the particle in unit time is under root 2 times of U average. So this is the volume covered by the hypothetical sphere in unit time. And then we can use unitary method like capital V volume n particles, unit volume n by V particles. So in this volume, how many particles are there? Right. So when we have done the derivation, it is more easy to remember the formula, right? If I have to write Z1, I will think what is the volume covered. So collision cross sectional area into actual speed, root 2 times of U average into number of particles per unit volume. So this is the number of collision by one particle in unit time. Now they can frame question. If you remember the formula, you should also know that number of particles per unit volume. By using ideal gas equation, you can write that number of particles per unit volume is equal to P by KT. K is Boltzmann constant, number of particles per unit volume. Average speed, you know, average speed is equal to under root 8 upon pi RT by M. So there are many chances to frame question based on this, that if the process is isochoric, how the collision number is dependent on temperature. So if N by V is constant, isochoric gas particles are fixed, volume is fixed, so N by V is fixed. So this is fixed. So it only depends on under root temperature. We can say that collision number is directly proportional to under root T. अगर process isobaric है, for isobaric process we can say that pressure is constant, volume is directly proportional to temperature. So if we put all these values here, this is average speed and this is number of particles per unit volume. So P by KT. Pressure is constant here. So how it is going to vary with temperature? You can say it is inversely proportional to under root of temperature. So be careful about all these things. They can frame questions about isothermal process. You can put N by V is P upon KT and you can simplify it, right? So for isothermal process, that is directly proportional to pressure. For adiabatic process, there are many equation, you know, adiabatic reversible process we are talking. PV to the power gamma is constant, TV gamma minus 1 is constant. Same way you can tell about Z1 by using this equation depending upon what is the data given. So first is collision number. Now we have to calculate what is collision frequency, which is the total number of bimolecular collision by all the particles in unit time and unit volume. Z1 is for one particle. If we multiply all the number of particles, right, why the factor of half is coming, we can explain it. Suppose we are saying that there are four particles, 1, 2, 3, 4, all the particles are identical. Then one, I can find out how many ways one can collide with the other particles. So there are three ways. One can collide with 2, one can collide with 3, or one can collide with 4. Similarly, I can write for 2, 3, and 4. Now here 1 is colliding with 2 or 2 is colliding with 1 is the same thing. We are counting the same thing 2 times, and that's why a factor of half will come. If we multiply Z1 into N, we are counting the same thing 2 times. That's why a factor of half will come. So this is representing total number of bimolecular collision in unit time. For unit volume, we should divide it by V. So now if I have to write what is Z1 in mind, I will think, okay, so there are collision by one particle in unit time, there are n particles, but we have take a factor of half and then we divide by number of particles per unit volume. For this Z1, we'll think that, okay, collision cross sectional area is pi sigma square, average speed is root 2 times of U average, and then number of particles per unit volume. So number of particles per unit volume whole square is going to come. Now again the same type of question they can frame, that for isothermal process, isobaric process, isochoric process, like same way you have to answer. You should know that N by V is equal to P upon KT. So that is an important thing. Mean free path. What is mean free path? It is the average distance traveled by a molecule between two collisions. Suppose this is the particle, it will move for a distance and it will collide and change its direction. Again, it will move for a distance, again it will collide and change its direction. Between these two collisions, this is a straight line, free path. Nobody is there. So this is mean free. Mean means this distance is different, this is different, this is different. So we have to find out the average distance traveled by the particle between two collisions, right? So what we are doing, total distance traveled by a particle in unit time, that is equal to average speed, divided by total number of bimolecular collision by one particle in unit time, that is collision number. So U average upon collision number is mean free path. And if we put here Z1, we remember pi sigma square root 2 average, right, into N by V. So U average will cancel out. It depends on number of particles per unit volume. If number of particles per unit volume will be constant, this mean free path is going to be constant, right? So these are the things related to it, right? So we can solve question based on mean free path also. So this is a question, ये JEE advanced screening मेंस में ये क्वेश्चन पूछा गया था इन JEE advanced. So assertion reason type of question है, the pressure of a fixed amount of an ideal gas is proportional to temperature. That is correct. We say that PV is equal to nRT. So fixed amount of gas means N is constant. And if volume will be constant, we can say that pressure is directly proportional to temperature. So this statement is true. Frequency of collision means we are talking about Z11. And अभी हमने पढ़ा कि Z11 is equal to what? Half into number of collision by one particle in unit time into capital M, total number of particles, divided by volume N by V. And if we further simplify, we can write half Z1 can be written as pi sigma square into under root 2 times of U average into number of particles per unit volume. दो बार आएंगे तो ये हो गया number of particles per unit volume whole square. So they are saying frequency of collision and their impact both increases in proportion to the square root of temperature. So while writing this, if we are saying the number of gas particle is fixed because nothing is mentioned, we have to assume, and the container is present, the rigid container is there, volume is constant. If this is constant, then we can say that Z11 is directly proportional to U average. And we know that U average is directly proportional to under root T. So Z11 is directly proportional to under root 2. This is fine. Impact of collision, frequency of collision and impact of collision matlab we know that 2 into m into v, that is impact of collision. So if we try to simplify this, 2 into m, if I want to write the speed, because this is the mass of one particle, right? We know that average speed, if I am writing average speed is equal to under root 8 upon pi RT by capital M. If I want to write this average speed in terms of small m, capital M is small m into Avogadro number. R upon Avogadro number is Boltzmann constant. So here I can write 8 upon pi. This is K into T by small m. So again we can say that the impact, that is 2 into m into v, is directly proportional to under root T. So this is also directly proportional to under root 2 and this is also directly proportional to under root T. So this statement is also true. But pressure of a fixed amount of an ideal gas is proportional to temperature. That is not explained by this collision frequency or impact of collision, right? So they are two independent statements. So both are true, but they are not the first. Second is not the correct explanation of first. So that's why answer is B. This is also a question 2016. The diffusion constant of an ideal gas is proportional to its mean free path and mean speed. So we don't know what is diffusion constant, but in JE they have mentioned that diffusion coefficient is directly proportional to mean free path, that is lambda, and mean speed u average. The absolute temperature of the gas increased by 4 times. So T2 upon T1 is equal to 4 and the pressure P2 upon P1 is equal to 2. As a result, the diffusion constant of the gas increases x times. So we can say that diffusion constant at temperature T2 and pressure P2 upon diffusion constant at temperature T1 and pressure P1. If we write, we can write that this is equal to lambda 2 upon lambda 1 multiplied by U average 2 upon U average 1. If I have to write what is lambda 2 upon lambda 1, lambda is written as U average upon Z1. The value of Z1 can be written as pi sigma square into under root 2 times of U average into number of particles per unit volume. So this U average and U average will cancel out. Same gas is there, so sigma square will cancel. These constant will cancel out, right? So the variable will be number of particles per unit volume, which can be written as P upon KT. So we can say that lambda is directly proportional to here temperature and pressure will come. So if we try to write lambda 2 upon lambda 1, that is equal to T2 upon T1 upon P2 upon P1. So T2 upon T1 is 4 and P2 upon P1 is 2. So this ratio will be 2. Lambda 2 upon lambda 1 will be 2. Same way you can write about average speed since the gas is same. So it is directly proportional to under root of temperature. So we can say that this is equal to under root T2 upon T1. So which is equal to 2. So if we put these values, we are getting that this value is equal to 4. This is also JEE advanced question, and this is a question based on Graham's law of diffusion and collision theory. So X and Y are two volatile liquids with molar mass 10 gram. Hello. 10 gram per mole and 40 gram per mole respectively. And cotton wool soaked in X and cotton wool soaked in Y. So the first question is very easy. It is based on Graham's law. We know that Graham's law of diffusion under identical condition, this is happening. So we can say that this is directly proportional to rate of diffusion of gas X upon rate of diffusion of gas Y is equal to under root of molar mass of gas Y upon molar mass of gas X, because the conditions are identical and molar mass of gas Y is 4 times molar mass of gas X. So this is equal to 2. Rate of diffusion of gas X, it is the distance traveled by the gas X in unit time. So that distance is D. For gas Y, it is total distance is this. So this minus this will be 24 minus D, which is equal to 2. If you simplify this, you can simplify that D is equal to 48 minus 2 times of D. So 3 times of D is equal to 48, or D is equal to 48 divided by 3. You can simplify this. I think 16 will come. So C option will come. This is an easy question. So most of the students are confused in this. So let me explain. The experimental value of D is found to be smaller than the estimate obtained using Graham's law. When we are talking about Graham's law, suppose from theory we got that at D distance here, which is equal to 16, we have calculated, right? At 16, this distance is in centimeter. This is the theoretical value. But when we do the experiment, from experiment, we come to know that this value is less than 16 centimeter, right? This is the experimental value. We have to tell that why the gas particle is moving slowly here. So already a inert gas is present here. When the gas particle, X gas particles are moving, they are colliding with this inert gas. If they will collide more with this inert gas, they will move more slowly. So it is related to collision of X gas particle with inert gas. And since the gas particles are moving slowly because they are colliding more with the inert gas particles, that's why the distance traveled by x gas particle is less with respect to y. So if we go through the option, increase collision frequency of y with the inert gas as compared to that y nahi, x is colliding more, so increase collision frequency of x with inert gas as compared to that with y, with y with the inert gas, right? Y is colliding less, collision frequency of y is less, that's why it is moving fast. Collision frequency of x is more, that's why it is moving slow. So that can be explained by collision frequency.
सर इसमें मतलब बी ऑप्शन क्यों गलत है? मतलब बी ऑप्शन भी लॉजिकली तो सही लगता है.
Explain why B option looks, because if we say mean free path is the distance traveled by the gas particle between two collisions. Mean free path is like that. अभी हमने मीन फ्री पाथ के लिए निकाला कि अगर वॉल्यूम कांस्टेंट है और नंबर ऑफ पार्टिकल्स कांस्टेंट है, देन मीन फ्री पाथ विल नॉट गोइंग टू चेंज. इनर्ट गैस फिक्स है इसमें, है ना, इसका वॉल्यूम फिक्स है, right? So there is no reason about mean free path, because number of particles, mean free path is directly proportional to number of particles per unit volume. These are not variable, these are not changing, so we cannot say about mean
हाँ
free path.
समझ गया सर, समझ गया.
Okay.
नहीं पर डायमीटर अलग हो सकता है ना दोनों का, एक्स और वाई गैस का.
ये है, they have mentioned ना here equal diameters, equal
ओह
molecular
सॉरी सर, ठीक है,
diameter.
समझ.
दिस इज द लास्ट क्वेश्चन, है ना. आज जो टाइम है हो ही गया है, बट इसको मैं शॉर्ट में डिस्कस कर देता हूँ. कॉन्सेप्ट ये वैसे थर्मोडायनेमिक्स में भी पूछा जा सकता है. पहले ये जो पिस्टन है ये इंसुलेटेड था, लेकिन अब इसको हटा के वी हैव पुट पिस्टन इन थ्रू विच हीट कैन मूव, राइट. तो पूरे सिस्टम के लिए अभी भी ये इंसुलेटेड है, तो पूरे सिस्टम के लिए क्यू विल बी जीरो. पूरे सिस्टम में कोई वॉल्यूम चेंज नहीं हो रहा, अंदर वॉल्यूम चेंज हो रहा है पर पूरे सिस्टम का वॉल्यूम चेंज नहीं हो रहा है, तो वर्क डन विल बी जीरो फॉर द होल सिस्टम. सो फॉर द होल सिस्टम डेल्टा यू विल बी जीरो. फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स पूरे सिस्टम के लिए लगाया. यहाँ पे गैस के नंबर ऑफ मोल्स एन ए, यहाँ पे गैस के नंबर ऑफ मोल्स एन बी. गैस विल बी सेम गैस है यहाँ पे. तो वी कैन से दैट डेल्टा यू इज इक्वल टू डेल्टा यू वन प्लस डेल्टा यू टू. Delta U1 is number of particles of gas A, and gas is same, so CV will be same. T final both same होगा. T लिख देता हूँ, माइनस टी इनिशियल इज 400, और ये T1 लिख देता हूँ मैं यहाँ पे, या TA लिख देता हूँ. I can write here this is TA, and this is number of gas in this container into CV सेम होगा, फाइनल टेम्परेचर सेम होगा, और ये TB है. This is 0. So if we simplify, you can write that final temperature is equal to NA plus NB TB upon Na plus NB. So by using that, you can find out what is the final temperature, right? Number of moles of A you can find, that is PV upon RT, pressure, volume, राइट. इसी यूनिट में मैं लिख रहा हूँ R इंटू टेम्परेचर इज 400. सिमिलरली यू कैन राइट नंबर ऑफ मोल्स ऑफ B इज इक्वल टू 1 इंटू 3 इंटू R इंटू 300. दिस इज Na and B. यू कैन पुट हियर नंबर ऑफ मोल्स ऑफ A and B गैस इज नॉट चेंजिंग. तो जब आप ये वैल्यू रखोगे तो यू आर गेटिंग दैट टेम्परेचर इज इक्वल टू 3200 डिवाइडेड बाई 9 Kelvin. देन यू कैन राइट दैट टेम्परेचर पता चल गया. हाउ वी विल कैलकुलेट फाइनल प्रेशर? तो इस पूरे प्रोसेस में, for ideal gas participating in any process, you can write that PV upon T. PV is equal to nRT, right? PV is equal to nRT. तो nR कांस्टेंट है, P1 V1 upon T. यहाँ पे नंबर ऑफ मोल्स नहीं चेंज हो रहा है, ये यूनिवर्सल गैस कांस्टेंट है. प्रेशर वॉल्यूम टेम्परेचर यहाँ चेंज हो रहा है, यहाँ भी प्रेशर वॉल्यूम टेम्परेचर चेंज हो रहा है. So for the whole system you can write that PA VA upon TA plus PB VB अपॉन TB इज इक्वल टू फाइनल प्रेशर. क्योंकि ये पिस्टन अब मूवेबल है तो फाइनल प्रेशर सब दोनों तरफ सेम होगा. P वॉल्यूम जो है वो VA हो, VA डैश लिख देता हूँ यहाँ पे, अपॉन टेम्परेचर फाइनल T होगा, प्लस P फाइनल इस कंटेनर के लिए VB डैश लिख देता हूँ यहाँ पे, और टेम्परेचर फाइनल दोनों जगह सेम होगा. So from here I can write that this is P final, and VA dash plus VB dash will be 4 meter cube. ये 4 meter cube हो गया upon final temperature. So now you know this value. You can calculate what is P final. तो आप जब P final calculate करोगे, value of P final will come 2. And now for this you have to calculate the volume. So you can write PV is equal to nRT. So V final of gas A, if you write, that is number of moles of gas A, R into T final upon P final. Right? Na, you know, Na you can put from here. Temperature you have calculated. Final pressure you have calculated. If you simplify, you'll get that the volume is equal to 2.22 liter or meter cube. Right? So this is there. So in the next class we are going to discuss about real gas. Real gas के बारे में discuss करेंगे. आज इतना ही. ठीक है.
So these notes, will we get it?
I will share. Definitely I will share the note. और कुछ पोर्शन रह भी गया वो भी, क्योंकि टाइम लिमिटेड है ना. आई विल शेयर ऑल द थिंग्स विच आर इम्पोर्टेंट.